So we can understand magnetism by drawing some analogies between magnets and something we already know a lot about, something called charges. A magnet consists of poles. If you've ever seen this in cartoons, every single magnet kind of has a north pole and a south pole, and you usually see this drawn as kind of like a bar. This is similar to charges, and the charges can either be positive or negative. Something else that's similar with charges is like poles repel and opposite poles attract. But the one big difference between charges and magnets is a charge, you can have positive charges or you can have negative charges, and they exist as separate entities. With magnets, you always have pairs. You always have a north pole and you always have a south pole. This is a fundamental result of electromagnetism, of some rules that govern how electromagnetism works. And basically, we can summarize this by saying there's no magnetic monopoles in nature. Conceptually, we can think of this as one of Maxwell's laws. These are the big equations, the big laws that govern electromagnets and electromagnetism. So no monopoles. So that means mono as in single, there are no singular poles. So if I take this magnet and I chop it in half, then I get a north pole and a south pole, but then those two poles immediately create their own little north pole and little south pole. So you get these two little bar magnets. So by cutting this in half, I can't isolate this north or this south pole. I just end up with two smaller bar magnets that each have their own north and south poles. So no magnetic monopoles. So a lot of summarizing that we have to do. There's two types of magnetism that exist out there. There are ferromagnetic materials. These are kind of natural magnetism. So we put that in kind of quotation marks, because it's based on the material that you have and how that material's electrons actually align themselves. So we have an alignment of electrons inside of a material determines how ferromagnetic that material is. Okay, now the alignment of the electron spins, this can be thought of a little bit as a natural electrical current inside of whatever material you have. So we're going to put this in quotation marks too. It's not strictly correct, but it's a good concept. It gets us close to understanding ferromagnetic materials. It's based on the natural electric current inside of your object where the electron spins. And we also have electromagnetism, electromagnets. Now these are magnets that you create by running electricity through something, and currents result in magnetism. This is a phenomenon that was first noticed by Ørsted when he held a compass up to a wire and it was deflected. And you could see this yourself if you take a compass and you hold it up next to an electrical outlet. So just one of those little three-pronged electrical outlets. If you just hold a wire up, hold a compass up next to this, what you'll notice is the compass, instead of pointing north, will be kind of shifted around. The little needle will shift just a little bit due to the electrical activity that's occurring inside of that electrical outlet. So you can see this yourself, and we have to take this into account when we're designing electronics. So this is done every day in creating cell phones, computers, TVs, any kind of thing that's carrying electric current. So another way that magnetism can be understood in terms of electronics is that magnets are similar to electric charges in that they also create invisible fields. So just like there's an electric field that emanates out from every positive charge, so that's a nice review. or an electric field that emanates into negative charges. There's a magnetic field that does similar things. Except magnets, we have a north pole and a south pole in every single magnet. So we have 2 poles. So the magnetic field lines that we get, they go away from the north pole and they go right back into the south pole. Okay. So the north pole is kind of like a positive charge and the south pole is kind of like a negative charge, in that your field line goes away from the north pole and it goes into the south pole. Okay. The other thing to note is, like the electric field, the number of field lines determines how strong your field is. So as I add more and more lines to this picture, this magnetic field is getting stronger and stronger. So I can represent a stronger magnetic field by drawing more lines. Now, how do we quantify this? How do we quantify a magnetic field? Now, to do this, we quantify the magnetic field in terms of the force that it can create. So we have the force from a magnetic field is equal to some charge that's going to be moving, basically to create a current, because we know magnetism is caused by currents, multiplied by the strength of the magnetic field that your charge is moving in. So that would be basically, in this picture, the number of, kind of proportional to the number of lines that you have inside of this field, times the sine of theta, where theta is the angle between your velocity, what direction your charge is going, and your magnetic field. So let's see what all these variables are. Q, remember, is the charge. V is the velocity of your charge, how fast it's going. And these kind of combine to give you an idea of what the current is, because the current is what is creating a magnetic force. It's creating a magnetic force for your object to feel. B is going to be your magnetic field. And theta is the angle between your velocity, how fast your charge is going, and your magnetic field, B. So if I take a magnetic field, let's create a magnetic field. I'm going to say that I'm going to create a magnetic field going this way. Magnetic field that's going straight down. And I'm going to take a charge and I'm going to send it moving into this magnetic field with some velocity. The angle between this velocity, which is going entirely to the right, and the magnetic field, which I've drawn, which I've chosen here just to go straight down, this angle right here is theta. So that could be 90 in this case. Maybe I've taken my charge and I'm kind of shooting it downward at an angle. So the angle between my V and my B would be this angle right here, whatever that is. So again, here's our magnetic force equation. This is a force that a charge feels moving in a magnetic field. We know pretty much all these variables and what they represent. We know that the units of the force, so the units of F, are going to be newtons. We know the units of Q. Units of Q are going to be units of charge, which are coulombs. We know the units of V. These are velocities, so that's going to be meters per second. And then the only unit we haven't talked about yet is the unit of B, the magnetic field. The SI unit of the magnetic field we call the Tesla, after a physicist named Nikola Tesla. And a Tesla is equal to 1 Newton divided by an amp times a meter. So again, there's that current coming into play in defining our magnetic field. Now, the magnetic field, this B, has some direction. Because the force has a direction, the magnetic field has to have a direction. And the direction of the magnetic field is one of the trickier things to figure out in physics. The direction comes from something called the right-hand rule. So the direction of a magnetic force. So you need to apply the right-hand rule here, which basically says you take your fingers and you point them in the direction of V. Then you bend your fingers so that they point in the direction of B, and then your thumb is going to end up resulting in pointing in the direction of F. This right-hand rule, it can be quite tricky to understand and tricky to play with and tricky to work through. So you should try to find some videos that actually demonstrate this and show you how the right-hand rule works. There are a variety out there, and you can find some good explanations of how to do that, of how to do the right-hand rule. One of the big uses that we have for magnetism and magnetic fields is to make objects change their path, to move charges around in a specific direction, in a specific way. And we can set things up so that magnets will move charges in big circles. There's some practical applications for this. We don't need to worry about those. What we need to worry about right now is how we can actually do that. So if we set up our magnetic field so that we can move in a circle, we can get a circle of radius r for a charge. We can make it move in a specific radius. That radius is going to be equal to m times v divided by q times b. Okay. Where m is whatever charge you're trying to move, the mass of that charge. V is how fast your charge is going. It's the velocity of your charge. Q is the charge of your charge, so how charged you are. And B is your magnetic field. There are lots of practical applications that we can use this equation for. Forcing particles to move in circles of specific radii. So using this process in physics, we use it in something called particle physics, and big objects called particle accelerators. To control beams of particles. It's also used in medical physics, in medical imaging, because again, we want to control where X-rays are going and these kinds of magnetic fields. And understanding how to manipulate how charges Q with certain masses move with certain velocities according to how big of a path that we send it through is very useful in medical physics and medical imaging. Now there's all sorts of other effects that we get from using magnets to accomplish things. So one effect in particular is something called the Hall effect. This is why using magnetism to accomplish tasks is quite tricky and requires a lot of care. So the Hall effect is when you get an EMF from a current carrying conductor in a B field. So if I have wires inside of a B field, say inside of an MRI magnet, I'm trying to take some patient images, I need to worry about the Hall effect, some back EMF. So if you remember the back EMF, this is basically voltage. So I have to know how this presence of a large current inside of a magnet is going to affect my patient. My patient has currents flowing through all throughout his body, and if I stick him inside of a big magnet, I'm going to have some Hall effect that I'm going to have to deal with or understand. It turns out that the Hall effect says that the EMF that's induced by current being inside of a magnetic field is equal to the size of the magnetic field you have times L, which is the width of your conductor that's inside of your magnetic field, times your speed V, which is how fast you're moving in that magnetic field. So this back EMF, I have to keep this in mind in medical applications when I'm sliding into an MRI magnet. Because this is basically what I'm doing. I've got a huge giant magnet. So there's my MRI tube. And I'm taking a patient And that patient is a conductor. That patient is a conductor that has a certain width. We'll call that width L. I'm going to slide this patient into this magnetic field. Now this patient is filled with electrons. There's all sorts of electric currents flowing through this patient's body. So he's going to create some electric current. So he's electrically charged. And when I send him into this MRI magnet, this magnet has a really, really big B field, big magnetic field. And if I slide him in really, really fast, then this high velocity is going to combine with this high magnetic field and give me a very high EMF that I will induce inside of this patient, and I could potentially damage them. So I have to be careful and be cognizant of these kinds of physics facts when doing kind of medical imaging, medical processes. So we don't only get magnetic fields and magnetic forces from individual charges, we also get them from wires. So magnetic field, magnetic force that's created by a wire is equal to the current inside of that wire times the length of the conductor, length of the wire that's inside of some magnetic field, times the sine of the angle between the I, the current, and the magnetic field B. So I here is the current that's inside of your wire. L is how much of your wire is inside of magnetic field. B is your magnetic field. And theta is the angle that exists between your current I and your magnetic field B. So let's say I set up a magnetic field. I'm going to have magnetic field going down, and I take a wire and I put this wire inside of that magnetic field. Now, parts of this wire are going to experience a magnetic force. The only parts that experience a magnetic force are going to be the parts that are actually inside of the field. Anything that's outside, anything out here, this isn't going to really feel that force because it's not inside of this B. So the current I is how fast the electrons are flowing down this wire, down this current. The length L is how much of this wire is in the actual magnetic field. B is the magnetic field itself. And theta is the angle that I have between the direction of my current and the direction of my magnetic field. So here it's 90 degrees. It would not have to be. I could have a magnetic field. We'll again draw a magnetic field going down. And I could have my wire kind of acting at an angle. Okay, so then I've got my current going one way. Let's try to draw that in red so that it pops a little bit more. And I've got my magnetic field going down. At the I and the B. And then the angle would be the angle between that I and that B. Okay, so that's the magnetic field that you can get, magnetic force that you can get inside of a wire in a magnetic field. You can also get some torque that happens on these wires inside of magnetic fields. If I put a wire inside of a magnetic field, I can make it spin, which is torque, back from physics 1. And the torque that you get inside of a wire is equal to N, which is the number of loops of your wire that are inside of this magnetic field, times I, times A, the area of your loop in a magnetic field, times B, times sine of theta, where theta is the angle between the area of the loop and the B field. So let's write down what all these variables are. N is the number of loops. I is the current. A is area. And B is magnetic field. And theta is the angle between area of the loop. Again, we're going to put that in quotation marks because area of the loop, what does direction of area actually mean? And a B field. So what the heck does this actually look like? Let's draw a magnetic field. In this case, I'm going to draw a magnetic field that's going to the right. So there's my magnetic field. And then I'm going to take a loop of wire. I'm going to take a loop, a coil of wire. And I got several loops of wire inside of this magnetic field. Let me make my magnetic field a little bit bigger so that this whole loop of wire is inside of this. So there's my loop, and N is the number of actual loops that I have. So if I look at this, I've got 1 loop, 2 loops, 3 loops. I have 3 loops of wire, so in this particular picture that I've drawn, I would have an N that's equal to 3. I is the actual current that's going through this wire. So there's a current that's going down in this wire. That current is I. A is the cross-sectional area of this loop. So if I take this whole picture, I'm looking at this from the side. Now if I could imagine like taking a wire, taking this loop, and instead of looking at it from the side, I come around and I look at it from just this side. So I'm going to imagine that I'm drawing an eyeball that's looking at it from this side. It's going to look a little bit different. I'm not going to see this magnetic field. I'm just going to see this loop. That loop's just going to look like a circle. So that circle is the area that I'm talking about. It's the cross section as I'm looking down, kind of if I looked at this from the right, from the left-hand side. It's just the area of whatever your loop is. Okay. In this case, I've got a circular loop, so I would have pi times the radius squared. The magnetic field is the magnetic field, just however big this is, however many lines I see here. And then the angle between the area and the B field. So this is a little bit weird. The area has an actual direction. So how can I figure out the direction of the area? The direction of area is always perpendicular to the surface area. If I look at this, this is a circle. I can imagine the surface area is pointing 90 degrees out from that. So the surface area is either parallel or anti-parallel to the B field. That takes some getting used to. That takes some reading. So look at your textbook and try to find some YouTube videos describing finding directions of area if that doesn't make any sense. So until now, we've really discussed how to find F when I know what B is. But how do I find B? Well, I know that B is produced by current. So B is produced by a current, and B from a wire, because wires are usually what you use to carry current, is equal to mu naught times the current divided by 2 pi times r, where r is the distance you are from your wire. You might recognize this. This is circumference of a circle. There's a reason for that. So I can find the magnetic field by taking these numbers, mu naught, which is a constant, I, which is your current, divided by 2 pi times r. R is the distance from your wire that you are. And I multiply all these numbers together and I get a B. I get a magnitude for B. But direction comes from the right-hand rule. And we're going to use something called the second right-hand rule. So the second right-hand rule says that you point your thumb, goes in the direction of your current. And then what you need to do is you need to bend your fingers 90 degrees. And at that point, the fingers will point in the direction of B. So let's see how that works. Let's try to visualize this. So I have two pictures here. This is the same situation. Here I'm looking at a side view. So I'm looking at a wire where I have current that's going up, and I want to think about an overhead view of this. So I imagine my eyeball up here looking down on this, and this is what I'm going to see. I'm going to see this circular wire, and I'm going to see some current. That current is coming out towards me, so I draw that as a little dot. That little dot represents something coming towards you. So a dot is towards you, or outside of the page, or outside of the video towards you. And an X would represent the opposite. That would represent something moving away from you. And this is kind of like, imagine an arrow. So if an arrow is coming towards you, you're going to see the little point. If an arrow is moving away from you, you're going to see the little feathery back. Okay. So what I would do to figure out the direction is I would take my hand, and I'm going to kind of draw a little sketch of my hand. And I'm going to have my thumb pointing out towards me. So here's my hand, and my thumb is pointing kind of up. So here's my thumb, there's my fingers, and my thumb is pointing up. So from a side view, this is what I see. I see my thumb pointing up towards me. And then here's my fingers, kind of fist, making a little fist. So here's my thumb portion pointing out. And then if I look at my fingers, from an overhead view, my fingers are actually pointing over in this direction. So here's all my fingers, kind of pointing over to the left. So my magnetic field here is going to be pointing to the left. But then if I take my hand and I rotate it around, if I rotate my hand around so that I'm over on this side, so here's my thumb is still pointing out. Now my fingers are going to be pointing down. So here's all my fingers. I'm clearly an excellent artist, but here my fingers are pointing down. I can do the same thing. I can rotate my whole wrist, my whole arm, so that I get down to the bottom. I have my thumb still pointing out of the page because that's where the current is going. And my fingers are going to be pointing now over to the right-hand side. So my magnetic field is going to be pointing to the right-hand side. And then we should be able to figure out that my magnetic field would be pointing up over on the right-hand side of this wire. So my magnetic field kind of draws a circumference around this circle. It draws around the edge, all the way around, tangent at all points, kind of pointing in a counterclockwise direction for this particular situation. I could draw this in the side view as well, except in the side view over on the right-hand side of the wire, my fingers are curling into the board, so my magnetic field is being a little dot going into the board. So I can draw that as an X. And then over on the left-hand side of the wire, my magnetic field is coming out of the board, so I would draw a circle with a dot. Okay, so this is the right-hand rule. This is the second right-hand rule for figuring out direction of magnetic field of a long straight wire, which is mu naught I divided by 2 pi r. And now hopefully we can see where this 2 pi r comes from. This is the circumference of a circle, which is the path that you trace out when you have an overhead view of the magnetic field created by this wire. So this is this circumference. I'm getting the magnetic field at any distance r away from this wire. Now occasionally you don't have a wire, you have an actual whole loop. And B from a loop is very, very similar. So B from a loop of wire is going to be equal to mu naught times I divided by just 2 times R. You don't need to worry about the 2 pi R. You just do the 2R. So this is from a whole loop. You can go look in the textbook to figure out what this kind of picture actually looks like. I would recommend doing that. And the last thing to make note of here is something called a velocity selector. This is one of the most useful things that we use in all of physics, and it combines electricity and magnetism quite nicely. So we have a charged particle that we move into an electric field. So we can make an electric field by making 2 parallel plates. I make one plate positive, I make one plate negative, so that creates an electrical field. Electric field, we should remember, points from positive to negative. Electric field always points away from positive and towards a negative. Okay. And then I can create a magnetic field that goes along with this electrical field. I can put this all inside of a magnetic field. Let's say a magnetic field that's going to go into the board. So a magnetic field that's going away from us at all points inside of this picture. Okay, so then I take a charge. Let's say I take a positive charge. And I can write the forces that are going to be felt by this charge on this velocity selector. And if I want this charge to get through this area completely unscathed, if I wanted to travel straight through, I can figure out how big of a B I need and how big of an E I need, and how big of a velocity I need for this to actually pass through completely undeflected. And I can do this by using some simple force analysis. So I can look at, there's going to be 2 forces occurring on this charge. I have a positive charge and it's moving inside of an electrical field. It's going to be attracted down to these negative charges and it's going to be repelled by these positive charges. So it's going to feel what we call the electrical force. And I know that electrical force is equal to Q times the size of an electric field. That's from previous chapters. Now I'm also going to feel a magnetic field. I can figure out the direction of the magnetic field by using the right-hand rule. I take my fingers and I point them in the direction of V. So my fingers go in the direction of the V, of the velocity. They're going to the right. I bend my fingers in the direction of B. So I bend my fingers so that they go into the board. And then it turns out that when I do that, my thumb is going to be pointing up. And that gives me the direction of the magnetic field. Practice this. Make sure that you can figure out how that works. And it gives me a magnetic force that's going to be directly opposite to my electric force. And the size of that is going to be Q times V times B. This is the definition of magnetic force. So if I want this to pass through undeflected, then I want the FB to be equal and opposite to the FE. So if I do that, I can set them equal to each other. QE has to be equal to QVB. I can notice I have the same Q. Q doesn't matter. It doesn't matter what charge I have. So to pass a particle through undeflected, I can find that the velocity I need is equal to the electric field, however big that is, divided by the magnetic field. This allows me to control how charges move inside of electricity and magnetism. It's very, very useful for all aspects of physics.